So I'll go through the basics of planning a LiDAR flight mission. Then we'll take a mid-morning break and then get into Lychee after that. Kind of go through that background information. Okay, so we got the sensor integrated now. It's on our drone, and we're ready. We're good to fly. We just need to plan our mission. There's some aspects that you'll want to consider, or that you can adjust depending on the type of projects that you're flying with your TrueView system. I'll go into some detail on these next, then I'll show you a mission planning spreadsheet that we have. So I'll have some slides on here that are kind of the background math, but we really don't need to get into it too much because we have a spreadsheet that kind of does it for you. The spreadsheets I show are for the 620 and the 410. So this is our older systems. We're kind of in the middle of updating them, but the similarities, at least for the mission planning, will be very, very similar. For the 635, 640, you can use the 620 planning sheet, and then for the 515, you can use the 410. The only thing on that is the points you'll be getting on the spreadsheet for that will be lower than what the 515 gives. So that's about 3 times more than the 410 for the 515. So you just multiply that and you get that value. We'll be adding those fairly soon. These are newer products, so we've got a little bit of time on those. So usually the first question, or sometimes the first question that comes up, I kind of explained it already, about the cameras is, it's not just a LiDAR sensor, but we do have those cameras integrated, and we want to know what about those for when you're planning a flight. Like I mentioned, we're with the field of view that we're using, and the reason we're picking these cameras in general is because the values aren't changing. They're fixed focal length, good mapping cameras, auto triggered. You don't have to really deal with anything with the cameras. They'll do everything on their own. So with most typical flight speeds, you're going to get pretty decent forward overlap. And what that means for the purposes of mission planning, if you're for a TrueView mission, is that the cameras are essentially fire and forget. You don't have to plan for those. We're not planning a photogrammetry, we're planning a LiDAR mission. And you can focus on that. Since our field of view for the LiDAR is going to be, or at least what we're processing is smaller than that 120-degree field of view, we're really planning for the LiDAR, and our cameras will cover all our area and then some. So for mission planning, it's just going to go out and collect images, and with these constraints, we're going to, with our LiDAR constraints, and then we'll have that oblique imagery as well, and as part of that data delivery, so I don't have to worry too much about them. So we're talking about LiDAR. The first place we'll, it feels a good place to start is actually, I prefer to start with flying height. Flying height's kind of the typical place you'd start. And as I mentioned, the specs that we put on these feels effective. Mapping height, 75 max for the 410, recommend 60 meters, 100 meters for the 600 models, flying, lower, 70, 75, 80 meters. Of course, you want to fly a little bit lower. Can we change the trigger interval on the cameras? Let me check. I'm not 100% sure on that, but it's every 2 seconds, so it's typically with the flight speed we've got. You don't have to, but let me check real quick. So I don't believe you can, with how they're set up at least, is they're set up for every 2 seconds. I will do a little bit more. I'll write that question down and get back to you though. I'm not 100% sure. I see a value in the configuration where it's set, but I don't know. I've never personally changed it myself. Never really found a need to with how we're flying at least, but of course everybody has their own types of missions, so there certainly is a possibility that you may need something like that. Back to flying height, 515, max we're saying 80, flying typically 60 to 70 meters or so, typically. Of course, these can change, and I'll go over some common settings and some things about that later. You'll start to get a sense, I think, as you do more flights with your specific hardware and sensor, and how these range parameters really are, are practical for your type of application and your type of work. Because depending on your application, what you're trying to do with your data, you may find that you can fly a bit higher, accept a little bit loss in detectability, a little bit less point count, or you need to fly lower because you got to get through thick canopy, these kind of things. So generally, flying height is where you start within that operational envelope of the system. Obviously, lower you fly this with the same scan angle, the smaller your swath width and your cross-track width becomes. So you'll have less coverage. That may mean you need to fly more lines. As mentioned, 60 meters for the 410, 75 meters maybe for the 600 models. Similar, maybe in between. I'd say in between for the 515, 70 meters or so. No reason to change. I think this is a good place to start. Nice ranges for at least how we fly them personally. So scan angle. All the sensors are 360-degree scanners, so they are continually rotating through the full 360 degrees, firing the laser for that whole 360 degrees. So what do we really mean about scan angle? These aren't systems or where they've got scanning mirrors that go side to side or anything like that. We think of scan angle in terms of true view as the angle off nadir to which we're going to limit the data. So what we're going to process, that's kind of the scan angle. So we can collect up to that 360 degrees as mentioned, but of course you generally don't want to do that for various reasons. I do have a question about flying lower. Flying lower, I think the advantages would be, with things like canopy, you'll have a better chance for those returns to get back to the system with a higher energy, and you can get through that canopy a little bit better. Another application may be something like power lines, something that's thin. You'll want to be a little bit closer to them so you have a better chance of getting that data back to the sensor. Those are just a couple examples, but that's I think that would be some of the more typical applications. And we kind of go over some general settings for, say, like thick canopy that I'll talk about. I'll give you a little bit more information on that. So like I said, scan angle is the angle off nadir, which we're going to limit the data that we're going to process. So that's typically how I think of it, at least, as what we want to clip the data back to. Because one of the trade-offs you make as you go to a larger and larger scan angle, and, you get further and further off nadir, it doesn't impact accuracy of the data. It can also impact things like canopy penetration and so forth. Generally, the rule is you want to keep the scan angles relatively narrow compared to the 360 degrees for airborne applications, at least. If this is a mobile application or a terrestrial application, that'd be a different discussion. But we do give the user the ability to control this to some degree through the configuration files and through Evo itself. So although the laser is always going to be scanning 360 degrees, you can limit on board what's collected in those ranges and what is actually written to the data file as you're collecting the data. The default for this is plus or minus 60 degrees. So that matches that 120 degree field of view for the cameras. Also, I don't know if I explained it too well, but what I mean by the system is always scanning 360 degrees. We are only writing the ranges of that plus or minus 60 degrees to the UMS as we fly. So we just don't even record the other ranges. Like I said, you can adjust this, but this is how it typically operates. As I mentioned, if you wanted to change this, you certainly can. Some of the practical aspects or practical situations you may want to do this is maybe you're trying to do a vertical structure like a bridge or a seawall. If you're flying kind of low and close to it, you may want to open that up so you can scan up it, up into the bridge deck, as well as some of the superstructure of a bridge, or if it's a seawall, it's just that vertical face. You may want to scan up closer to that plus minus 80 degrees, plus minus 90. It just depends on your application, and it's could use some testing on your part if you want to make sure you can get usable data from that. We haven't done I haven't personally done a whole lot of vertical scanning. Most all my missions have been mapping, but this is an option. So the scan angle is what we record, and what we'll further clip in Evo down to typically plus or minus 40 degrees, as shown here in the software. You just got to be aware the further off nadir you can get less accuracy. There's an error component that is tied with that off nadir angle. Also going to impact things like canopy penetration. This is just general default. If you don't want to tweak this too much, plus or minus 40 is good for all of our models. I'll go back to line spacing. So line spacing, this is going to be our last aspect we'll talk about for mission planning before we kind of get into some of those other, some of the more, besides the actual planning. So this is basically the distance between the flight lines. We want to plan this, of course, to avoid any gaps between the lines, because typically we're looking for 100% coverage. Typically means we're going to fly with some overlap, some side lap. That is data, of course, from each flight line that is actually going to overlap the flight line beside it by a certain amount. Typically, we talked about in terms of percent overlap, or percentage overlap, or percentage side lap. It's not really that different from traditional airborne LiDAR, or, photogrammetry. If you've done this, you've heard those terms, of course. The number of flight lines and the flight line spacing is going to be dependent on how high you fly, and what your swath width is, the area you need to cover, the scan angle you want to use, and the percentage overlap that you're going to use. The bigger you make the percentage overlap, the more lines you're going to need. The higher you fly, the less lines. The lower they fly, the more lines, of course. All the standard trade-offs that apply there. We'll talk about this a little bit more. Side lap, as I mentioned, is to make sure you have coverage, but it also can be important if you're looking at how well calibrated your system is. We'll talk about calibration more this afternoon. Look at post-processing the data, but just like any LiDAR system, preview units have a calibration, have a bore sight that basically is set to minimize any systematic error in the system. And one way we look at this is through the overlap areas, the side lap areas, for instance, to make sure that if data scanned in two different directions from two different flight lines, we want to make sure that data on at least on a flat surface lines up with each other. So really, this is just kind of for reference if you're having to work with calibration or looking at the calibration issues or fit of the data. This is just an area where side overlap is very important. There's tools out there to market such as TerraSolid, tools like TerraMatch, so forth, to assess that, but we won't get into that too much, just to be aware of. So with most drone LiDAR systems, you're collecting a fairly dense point cloud. With the TrueView 410, probably collecting about 100, 200 points per square meter. 600 model, it's going to be a little bit lower, about 100 points per square meter. The 515, it's going to be double, triple that of the 410, because it does have a lot more beams. 600 models have less beams, so they're going to be, of course, less points. That kind of goes into that multi-beam talk that we kind of mentioned. Of course, there may be situations just with traditional airborne LiDAR where you want to increase the density over what you're getting from a single pass. So slide lap can be a way to do that. I'll give a kind of more extreme scenarios. If you want to fly with 50% overlap, you're actually overlapping both sides of your flight line. You're essentially doubling your point density that you're collecting. If you're not really worried about any of that and just want to use a default number, we typically recommend something 30 degrees, maybe 25. It's getting a little lower. Typically, we'll fly with 33% is what our standard is. That's kind of regardless of the model as well. So when you think about your flight planning or your mission planning, that's kind of the process you go through. It's not different from planning any sort of LiDAR mission. You need to look at your project site, and then based on that project site, look at, for what I would start with, is flying height. Think what will be the needed for the best coverage, or maybe even what you're able to fly there, because of course some locations you're not able to fly so high. You may have to look at that first regardless, and then plan from that flying height, to get the coverage that you want, and so forth. There's a couple quick tools I'll show in a minute. We can look at some of those shortly. As you get more experience of flying, the TrueView system, a lot of this gets internalized. It becomes, you can look at a project and, yeah, I want to fly this at, say 50 meters, 15, 20 degree overlap, and get the kind of data that I can use. It's kind of an experience curve that as you do more flights, of course, you'll start to figure all this out a little bit without using spreadsheets and whatnot. That's just with anything, though. As you get more experience, of course, you'll be able to do this just in your head. So next you'll look at, of course, overlap, calculate that, look up that based on the point density you want to do, and then you want to go ahead and plan your mission. We'll skip through these. So side overlap, talked about that. And there's a bit of math. We talked about the recommended approaches. So this is kind of the math we're going through. It's nothing you have to worry about. It's all calculated for you. There's a couple lookup tables we have, such as this. This is in that spreadsheet. This was included in the data if you downloaded it in that TrueView documents folder. there's going to be a mission planning sheet called, let me see what the exact name is. It was called, TrueView Mission Planning version 1.7. That should be included. And that's what we'll look at next. Go ahead and pull it up. So it looks like this. I'll start with the lookup tables and then move on to more of the interactive part of it. Like I said, there's sheets on here for the 410 and the 600 series, soon to be added the 515, but using the 410, you can just up that point density by about 3 times, and that's about what you'll get. It'd be pretty close. So kind of just walk through this, and orient you to it. Sort of explain how we use it when we're looking at setting up a flight, plan for a project or an area that we want to go fly. And there are a fair number of tabs here, like I said. I won't go through in excruciating detail all of these, but I kind of just want to orient you to what they are and how to use them. The first two are really just simple lookup tables, and they're primarily just to you do a quick lookup. As I mentioned, more projects fly. Of course, this will become, you'll be able to do this in your head fairly easily, especially if you do fairly similar projects to each other. Of course, you can use the same settings. First one you want to look at, or that we're looking to look at, is line spacing. Generally, what this is going to do is if you look at the height that you want to fly, this is top section here in gray. That's altitude. And the scan angle over here. So this is what we're going to be clipping it to in software. So this is in half degrees. So in the software, this would be, you'll say 40 degrees, but of course this is plus or minus 40. So say I want to fly at that 60 meters with that 40 degree scan angle. This will be my swath width I'm getting from that. Now if I want to fly with the bottom part is with a certain overlap, this is set for 33%. If I'm wanting to fly at that same 60 meters at 40 degree, what our this gives us our line spacing that we need to set in our mission. So we'll be using roughly 68 meter line spacing, and I'll show you more of that, what that means when we kind of plan a mission. It's fairly straightforward, but this is here for a quick lookup. So the common sort of lookup we have here is for GSDs. This is more for the cameras themselves. I won't go into too much detail because it is kind of, at least with this section here, it's a little bit more in depth, kind of planning photogrammetry, but of course we're not specifically doing that, but this is a little bit more complicated with the photogram. But this is going to be our GSDs for specific heights. Of course, we're not flying at 2 meters, but it's just here for reference. Kind of gives you the GSD for our cameras. Now the field of view is not symmetric for the cameras, so you do get a separate cross track and a long track GSD. But say I'm flying out at 60 meters, I get about 1.5 centimeters by 1 centimeter pixel size. Flying at 60 meters, of course, with these cameras. It's going to just a quick look up, more detailed analysis. The more detailed analysis sheet, of course, are these point densities here. What I'll do is I'll start with the, since it's right here, I'll start with the 600 series. What we can do, what we've done here is we basically built the sensor model, all the parameters of the LiDAR from the manufacturer in terms of, rotational speed and a whole bunch of other things that go into the performance of the system. And we set it up so that you as the user can come in here and plan based on adjusting essentially, these values up top. It's 5 for the 600 and 4 for the 410, 515 systems. Essentially the same settings with the 600 series, of course, having that extra, it has an extra couple sections here. So what it'll do is, based on these parameters that we input, it'll quickly calculate for you, what is swath width, what is the line spacing. It'll also give you stuff like expected point density. So not considering multiple returns, 3 or 5 returns, so it's just you're going to put this down this many points per square meter based on the settings. Some users are going to be interested in digging down a little further to see what the point spacing is. Point space is going to be slightly different cross track versus long track, and also with the spot size, what the spot size may be. Of course, ties into the divergence of the laser beam itself. So you can do a pretty deep dive what kind of collection parameters you're going to have. Kind of just do all the math for you here. We also have some sections over here with like coverage estimates and flight duration. I haven't used this too much myself, but it is here if you want to take a look at it. So it works very nice, if you want to, dig into some of those metrics. I will mention for the 600 series, there is a setting in the core configuration file that you upload to the system that sets a parameter for the Regal system that is referred to as the angular step. Not something you have to mess with if you don't want to. And I'll try and find some documents for that and send that out to the 600 users to be able to get a little bit more in depth on that. But there, it kind of gives you a description here. Let me find it. Yeah, right here. Angular step. So there's a little bit of a description there, what this actually means. Generally what it applies is you need to tell the system how many degrees to move with each step of the system. What this really means for planning purposes is from our perspective of the user, if we set a scan rate, it will calculate for what the angular step width is. And this angular step width is actually the value that you'll enter in the core config, and I'll pull one up that way we can look at it. Another thing that is a little bit different with the 635, 640, anything is that if you want to have uniform point spacing, you need to be careful about what scan rate you set, so we can calculate that for you here as well. For instance, say if I want to let's make some changes here. I'll do flying height at 60 meters, speed 5 meters per second. That's typical for what we do. I'll drop my full view down to 60. Overlap, I'll use 33%. Frequency, I'll use 200. And what I'll do is I'll change this scan right here to 50. So what this tells me right away, you'll see that I input 50, but the actual value to do uniform spacing here is this number 51.503 here. So if I want to have uniform spacing, I'll actually need a little bit higher in my scan rate. I need to be at 51.503, so that'll give me equal spacing. And let me Let me see if I've got a core configuration here that I can show where that would be input. Like I said, this isn't something you have to do unless you're trying to do a bit more of a deep dive. It'll operate exactly as intended from factory as well. This is just for more of a deep dive. Let me see. Okay. So the actual value you're interested in to get this uniform spacing is this angular step right here. So this is the value you'll want to enter into your core configuration, and I have a core configuration here. If you go to section 11, you'll see where to go. This angular step is set here. You can change that here to get if you're planning for a specific type of mission that needs uniform line spacing. But I mean, the way we have these set up, they'll fly perfectly fine without changing any of this. Move over onto the 410. So this generally has the same stuff except for there's less you can input here. So I'm gonna go ahead and change this to say we'll change it back up to 33, flying at 65 meters, 5 meters per second. With that's typical flight. It'll give you some of these values for you. Like I said, with this average point density, I just multiply that by 2.5, 3. I'll say 2 to 3 times. That's about the 515, just because of the extra beam count. Very similar options here, but I'll give you some general recommendations here shortly after this. See if you don't want to even use this. I can give general settings, and what these general settings will most likely get, usually gets, depending on the project, will get you pretty good results. I'll show you some of the common settings that we would typically do on our service flights. So you do have a copy of this available. I believe it should be available on that our knowledge base as well. So that's support.goq.com. That should be there as well. Let me see the question you asked. Is the first pulse return spacing? Yeah, this is going to be first pulse return setting. This isn't going to be multiple returns. Isn't kind of including that in here. Use case for this. I don't know necessarily. I haven't used it for a particular case myself. But I haven't. I think this is just kind of some background information, gives you some of the extra information for you. Maybe as you start flying more, and if you mess with some of these settings, you could see where that gives you use. But I haven't. I don't know if that'll give you too much extra. I see what you're getting at though. Yeah, of course. Maybe if you're in an area where, hopefully that answers your question. But yeah, I don't know if I have a better answer for that, but. But if you have any issues with, if you're trying to use this later, you're trying to plan a mission, you don't remember anything I'm saying here, or you don't want to go back and watch it, what you can do is, I'd recommend is either calling in or sending a support ticket in, and we'll hop on with you and look this through with you, kind of give you some recommendations. You can give us what you're wanting to get out of the project, and we'll help you plan a mission if that is needed. But it's fairly straightforward, and I'll give some common settings here shortly. Chapter. There are some more charts here, but they're just more, or tabs here that they're just more math and conversions that we're using. Nothing you'll need unless you want to do more of a deep dive. Okay. So some useful, defaults. But I'll start with general purpose. I believe these are based on the 410, but I'll try and adapt them to the other sensors as we go. I mentioned a fair number of these before. General purpose, I'd say, plus or minus 40 degrees field of view. That's typically what we use. That's a good general purpose. Is more than adequate. 60 to 75 meter flying height, 60 meter for the 410, 75 for the 600 series, about maybe 70, so go in between with for the 515. Just a little bit down from the effective mapping range. Line spacing, it says 25% side lap here. What we typically use is 33. 25 would be still adequate for most cases, I'd say. But if you use 25, this kind of gives us an even line spacing of 75 meters, which is quite workable for a lot of projects. So this is a good general purpose settings. So this is what I recommend using for, say, you don't really want to tweak your settings much and you just want to fly site. This is what I would use. So the next one, if you want to maximize your coverage, so getting a lot flown in a smaller amount of time, you'll have a little bit less points on the ground, but you'll get more covered at once. So we're going to open that field of view up to plus or minus 50 degrees, flying a bit higher. So we'll fly at our max effective range. And you may, of course, want to do even some testing and fly a little bit higher than what I'm mentioning here, just to see what is relevant to you, and maybe your project doesn't need as much points on the ground, and you're good with slightly less density, and you can fly a little bit higher. You just gotta watch out for flying too high, because you'll start, of course, getting dropouts. It's just the nature of these units, of course. This gives us a 180 meter swath. We'll use that same 25% side lap. This gives us 135 meter spacing, so we can fly a lot more area in the same amount of time. It's kind of a max coverage. Of course, drone LiDAR systems, they're not, at least currently, they're not going to compete with the coverage on a, very large area of, like, say, a manned. You're really going to push the boundary of what you can do with the drone. Even with the, as we start getting to beyond visual line of sight and longer duration flights, there's always going to be areas large enough that cost effectively it's just going to be better to bring in a fixed wing or helicopter platform to get those max coverage, at least for some of these larger scale ones. So max coverage, at least in the context of drone survey, is what we're talking about here. The last one we have here, a thick canopy. We'll give you a couple general recommendations. So if you've got a lot of trees on your side or any kind of vegetation that you're trying to get through that, to that bare earth topography beneath the canopy, probably you will want to narrow your swath width down a little bit. That's just it's because, again, as you move off nadir, you lose canopy penetration. Flying lower helps, so it's the canopy penetration, because you're going to have more energy, like I said, in the pulses. That is, the pulse isn't going to have as much divergence, so you've got more chance of it getting some of that energy to the ground. So flying lower, flying slower, reducing your scan angle. limiting your view close to nadir, help with that canopy. Of course, this is going to really reduce your line spacing. You're basically trading off coverage for better canopy penetration. Canopy is one area where when you're working with customers, we do often find you do have a little bit of testing and benchmarking yourself, because of course canopy is a very generic term for something. There's a lot of wide variety of types and thicknesses and opening and so forth. So it is an area where you need to collect a little bit of your own domain expertise based on the type of projects you fly and the type of vegetation you're dealing with. On those projects, it's hard to come with a clear, hard, and fast guideline, but these are some good to start with. So plus or minus 30 degrees on the field of view, 30-meter flying height gives us a 35-meter swath, 25 side lap. Like it was 26. So we are significantly reducing our line-to-line spacing, but in efforts to get through that canopy. Okay, any questions about any of the flight planning or the basics on mission planning?
Have you done any experiments yet with thick low veg, like mangroves, or I guess where I work, we have a lot of thick sage, so that they kind of maybe 3 to 5 meter in height veg. If there's any different settings you're using for those type of environments?
Not personally. With that, these settings would work. We could actually probably, these are a little even more conservative, I'd say, for something like that. I think what we're going with here is just a heavy, more tree canopy rather than ground cover. But I guess, yeah, that's something that you may want to experiment with yourself. I haven't personally done a lot of vegetation cover in general, but I know with at least with the 515, with how many beam counts it is, these settings are probably incredibly conservative. It's just a newer sensor, so we haven't had a whole lot of testing with that yet. But as it matures a little bit, I'm sure we'll get a bit better recommendations for that. But yeah, that's something I would need to test.
Okay, thank you.
Yeah, no problem. With that, if nobody else has any questions, what I'll do for now is take a quick 15-minute break, and what we'll do when we come back is I'll go over mission plan, actually planning a mission. I'll use Lychee, kind of go over some of the important aspects with planning, as well as I'll probably jump ahead of myself with some of the flight operations stuff to introduce the heading alignment maneuver, because this is something that's fairly important, and you kind of have to, depending on the flight missions you're flying, you may have to introduce this into the mission plan itself. Besides the usual, what we do is do a heading alignment maneuver at the beginning and end of the flight. Depending on the type of mission, you may have to introduce that in the middle of the flight, but you can plan that into the mission so it'll do it itself. But I'll show you that more when we get there. But it is currently 9:40 Central Time. What we'll do is come back 5 minutes till 10 Central, so about 15 minutes, and then we'll move on to the actual mission planning. The recording. So I do have an answer for that 300 kilohertz question. So I have what I'll show. So this is what the core config for the 635, 640 will have it does have a selectable. There is a caveat with that. With the way the LiDAR works, it is a 300 kilohertz at 120 degree field of view, which is how we typically operate the system. So the way with that envelope, it does use that 300 kilohertz, but if you're opening up that 100 or 120 degree field of view, I think you'd have the way I understand it is it would have to be bumped down to 200 kilohertz. But it is in the normal operation of how we operate the TrueView systems, it is 300 kilohertz at 120 degree field of view. Okay. So let's talk about the actual flight planning. So what I have here on the screen is we're going to get a few background information. First, as shown here, we're going to want to do